C# and AI Masterclass by Edgar Milvis Volume 4, Chapter 2. Now, let's explore Chapter 2, the state machine, how async and await really work. Moving on to theoretical foundations. The async and await keywords in C# are often misunderstood as mere syntactic sugar for multithreading. While they do enable concurrency, their primary function is to manage the lifecycle of execution, specifically, how a method pauses and resumes without relinquishing control of the underlying thread. To truly master asynchronous programming in AI pipelines, where we often juggle hundreds of concurrent API calls, database fetches, and stream processing, we must visualize these methods not as linear sequences of instructions, but as state machines. Let's discuss the state machine model. In the context of the C# compiler, an async method is transformed into a struct or class that implements a state machine. This machine tracks the current execution point of the method. When a method is called, it begins in the pending state. As soon as the first await is encountered on an uncompleted task, the method enters the suspended state, yielding control back to the caller or the scheduler. When the awaited operation completes, the state machine transitions the method back to the running state to process the result. This transition is the heartbeat of asynchronous AI pipelines. Consider a scenario where an AI application needs to fetch context from a vector database, generate a response using an LLM, and then stream the result to a client. Without a state machine model, we might block a thread waiting for the database query, wasting resources. With the state machine, the method suspends during the I/O wait, allowing the thread to handle other requests, vital for scalability in high-throughput AI services. Moving on to the three core states. 1. Pending. The method has been invoked, but the state machine has not yet begun execution or is awaiting initialization. 2. Running. The state machine is actively executing code on a thread. This continues until it reaches an await expression. 3. Suspended. The await expression has been evaluated. If the awaited task is not yet completed, the state machine yields control. It captures its current location, the instruction pointer, and returns an incomplete task or value task to the caller. The method effectively goes to sleep, retaining its local variables and context within the state machine object. Turning our attention to the role of the event loop and task queue. The transition between suspended and running is not magic, it is orchestrated by the event loop, specifically, the task scheduler and the underlying thread pool. When an async method suspends, it registers a continuation, a callback that tells the runtime, when this specific task finishes, wake me up and execute the following code. In an AI application, this is analogous to a restaurant kitchen. The chef, the CPU thread, is cooking a complex dish, processing a request. If the dish requires an ingredient that is currently out of stock, awaiting an API response, the chef doesn't stand idle. Instead, they set a timer, registers a callback, and immediately start chopping vegetables for another order, handling a new request. When the ingredient arrives, the API response returns, the timer rings, the event loop triggers, and the chef resumes cooking the original dish exactly where they left off. This mechanism is crucial for streaming LLM responses. When we await a stream of tokens from an LLM, we are not blocking for the entire response. We are suspending after every token or chunk, allowing the event loop to process network I/O or other concurrent tasks. This creates the illusion of real-time responsiveness while efficiently utilizing a small pool of threads. Moving on to deep dive, the compiler transformation. To understand the how, we must look at what the compiler generates. When you write an async method, the compiler rewrites it into a state machine struct, usually a value type for efficiency to reduce heap allocations, that inherits from async state machine. Source code. Here, we're defining a public asynchronous method named getModelResponseAsync. This method is designed to orchestrate the retrieval of a model's response based on a given prompt. The async keyword is crucial here. It signifies that this method will perform operations that might take a significant amount of time and should not block the calling thread. The return type task string indicates that this method will eventually return a string, the model's response, but it will do so asynchronously, returning a task object immediately that represents the ongoing operation. This is a fundamental pattern in modern, responsive applications, especially when dealing with I/O bound or computationally intensive tasks like interacting with AI models. We pass a prompt as a string argument, which is the input query we want the AI model to respond to. At line 3, we initiate an asynchronous operation to fetch context async, prompt. This method is responsible for retrieving any necessary contextual information that might be relevant to the given prompt. For example, this could involve searching a vector database for similar embeddings, querying a knowledge base, or fetching user-specific data. The await keyword pauses the execution of getModelResponse@async at this point until fetchContextAsync completes its work and returns its result. Importantly, this pause is non-blocking. The thread is released to handle other tasks while fetchContextAsync is running. This is a cornerstone of asynchronous programming, preventing UI freezes in client applications or thread pool exhaustion in server-side applications. The result of this operation is stored in a context variable, which will likely be a structured representation of the retrieved information. Following the context retrieval, at line 4, we invoke another asynchronous method, generateAsync, context. This is where the core AI model interaction likely takes place. The context obtained from the previous step is passed to this method, allowing the AI model to generate a more informed and relevant response. For instance, if fetchContextAsync retrieved relevant document chunks, generateAsync would use these chunks as part of the prompt to the large language model, LLM, or as input for a retrieval-augmented generation, RAG, pipeline. Again, the await keyword ensures that the execution of getModelResponse@async is paused non-blockingly until the AI model has finished generating its response. This step is often the most time-consuming in an AI pipeline, and its asynchronous nature is paramount for maintaining application responsiveness and scalability. The generated response, typically a string, is then stored in the response variable. Finally, at line 5, after both the context fetching and response generation steps have completed successfully, we return the response string. This marks the successful completion of the getModelResponse@async method. The await keywords ensure that we only reach this line once all preceding asynchronous operations have finished and their results are available. This structured, sequential execution of asynchronous steps is a common and powerful pattern for building robust and efficient AI pipelines, where each stage might involve I/O, network calls, or intensive computation. The entire method effectively composes several asynchronous operations into a single, cohesive asynchronous workflow. Conceptual Compiler Output, Simplified. The compiler generates a struct containing fields for local variables, prompt, context, response, and an integer_state field. It also generates a moveNext method, implementing async state machine, which acts as the dispatcher. State -1, initial state. State 0, after entering the method, before fetchContextAsync. State 1, after fetchContextAsync completes, before generateAsync. State 2, after generateAsync completes, before returning. When moveNext is called, 1, it checks the _state field to jump to the correct label. 2, it executes code until an await is hit. 3. If the awaited task is not complete, it sets _state to the next step, registers the continuation, and returns false, indicating the method is not finished. 4. When the task completes, the runtime calls moveNext again. The switch statement jumps to the correct label, restoring local variables from the struct fields, and execution continues. Now, let's explore analogy, the librarian and the index cards. Imagine a librarian, the event loop, managing a stack of index cards, tasks. Each card represents a request for information. 1. Pending, a patron hands the librarian a card requesting a book from a remote storage facility, an I/O operation. The card is placed on the to-do pile. 2. Running, the librarian picks up the card and begins the process. They check the catalog, running code. 3. Suspended, the librarian realizes the book is in off-site storage. They don't wait by the phone for the storage facility to answer. Instead, they write a note on the card, call patron when book arrives, registers a callback. They place the card in a waiting tray and immediately pick up the next card from the to-do pile. 4. Resumed, when the storage facility calls back, the I/O completes, the librarian moves the card from the waiting tray back to the active desk and continues processing that specific request. In an AI pipeline, this allows us to manage thousands of concurrent requests. If we have a task. When all waiting for 50 different LLM generations, the librarian doesn't block on the first one. He suspends all 50, handles network interrupts, and resumes them as data arrives. Now, let's explore visualizing the state transitions. The following diagram illustrates the flow of an async method through the state machine, governed by the event loop. The diagram illustrates how an async method is decomposed into a state machine where the event loop suspends and resumes operations, pausing execution at each await point to handle network interrupts and other tasks before continuing. Now, let's talk about architectural implications for AI pipelines. Understanding this state machine is not merely academic, it dictates how we structure scalable AI applications. 1. Avoiding thread pool starvation. If we misunderstand await and treat it like a blocking call, e.g., using .result or .wait, we force the state machine to stay in the running state while waiting. This blocks the thread. In an AI server handling thousands of requests, blocking threads leads to thread pool starvation. The thread pool runs out of threads, and the application becomes unresponsive, even if the CPU is idle. By allowing the state machine to transition to suspended, we free the thread to process other requests. 2. Zero allocation optimization with value task in high-frequency trading or real-time AI inference. Every allocation matters. The standard task is a reference type, heap allocation. If an async method often completes synchronously, e.g., reading from a cached memory stream, we can use value task t. This is a struct, stack allocation, that wraps the result. If the operation completes immediately, it returns the value directly without instantiating a task object. This leverages the state machine's ability to handle both synchronous and asynchronous continuations efficiently. 3. Composing pipelines with async enumerable t. In Book 4, we deal with streaming LLM responses. The async enumerable t interface relies entirely on this state machine model. When we await for reach over a stream of tokens, the state machine suspends after every token yielded. This allows the consumer to process the first token while the rest of the stream is still being generated, enabling low-latency UI updates in chat applications. Now, let's explore connection to previous concepts, dependency injection. In Book 3, we discuss dependency injection, DI, and interfaces to decouple our business logic from specific implementations, e.g., swapping OpenAI for a local llama model. This decoupling is essential for testing and flexibility. However, introducing async requires careful handling of these interfaces. If we define an interface for an AI service, we must ensure that asynchronous operations are properly represented. Synchronous interface, inefficient for AI. Here, we're defining a fundamental contract for any component that wants to provide a language model's text generation capabilities. This model provider interface is a classic example of abstraction and dependency inversion, two pillars of good software design. By defining an interface, we decouple the consumers of text generation from the concrete implementation of the model itself. This means we can swap out different large language models, LLMs, perhaps one from OpenAI, another from Google, or even a local open source model, without altering the code that uses the model. This significantly enhances flexibility and maintainability. The single method, generate, takes a prompt string and is expected to return the generated text. Notice the comment // blocks the thread. This is a critical design decision and a warning about the synchronous nature of this particular interface. It implies that calling this method will halt the execution of the calling thread until the generation is complete. While simple for initial understanding, this synchronous blocking behavior can become a significant bottleneck in high-throughput or highly responsive applications, especially in web servers or UI threads. We'll see how this limitation is addressed in subsequent parts of the system. Asynchronous interface, scalable for AI. Here, we're defining a fundamental contract for any component that wants to act as a large language model, LLM, provider. This is an interface, model provider, which is a cornerstone of good object-oriented design and promotes loose coupling. By defining an interface, we're saying, any class that implements this interface must provide a method called generateAsync that takes a string prompt and returns a task string. This task string return type is crucial. It signals that the operation is asynchronous, allowing the calling thread to remain responsive while the potentially long-running model inference is happening. This is a best practice for I/O bound operations like calling an external AI service, preventing UI freezes or thread pool exhaustion in server applications. By defining the contract with task string, we allow the underlying implementation to decide how to handle the execution. Whether the implementation uses HTTP client to call a remote API, high latency, high suspension, or runs a local model on a GPU, low latency, potential synchronous completion, the consumer of the interface remains the same. The state machine logic encapsulated in the async/await keywords ensures that the consumer handles the result correctly without needing to know the implementation details. Turning our attention to edge cases and nuances. 1. Synchronous completion. Not all async methods suspend. If an async method performs purely synchronous work or hits an await on a task that is already completed, e.g., task.completed task or a cached result, the state machine might never leave the running state. In this case, the overhead is minimal, often just a state check. 2. Configure await, false. In library code, like the AI service layer, we often use configure await, false. This tells the state machine, when the awaited task completes, do not bother capturing the current synchronization context, like the UI thread context, to resume execution. Resume on any available thread pool thread. This prevents deadlocks in UI applications and improves performance by reducing context switching overhead. 3. Exception handling. The state machine also captures exceptions thrown within the async method. If an exception occurs during the running state, it is stored in the task, or value task, returned by the method. When the caller awaits this task, the exception is rethrown at the suspension point. This allows for standard try-catch blocks to work seamlessly across asynchronous boundaries, which is critical for robust error handling in distributed AI systems where network failures are common. Let's discuss summary. The async/await state machine is the engine driving modern C# concurrency. By modeling execution as a set of states, pending, running, and suspended, we can build AI pipelines that are both efficient and scalable. The event loop acts as the scheduler, managing the transitions between these states based on I/O completion. This allows a single thread to handle hundreds of concurrent operations, essential for real-time AI applications. Understanding this low-level mechanism empowers developers to write high-performance code, optimize resource usage, and effectively utilize patterns like async enumerable for streaming data. Now, let's explore basic code example. We begin by importing necessary namespaces. Notice how system, threading, tasks is crucial here. This namespace provides types that simplify writing asynchronous code, particularly task and task-to-result, which are the bedrock of C#'s async/await pattern. Without it, our ability to perform non-blocking I/O operations and manage concurrent work efficiently would be severely hampered, forcing us back to older, more complex callback-based or thread-based models that are harder to reason about and scale. Here, we define our main class, async state machine demo, and the entry point of our application, the main method. Observe that main is declared as static async task main, string, args. The async keyword is vital, it signals to the C# compiler that this method can contain await expressions. The return type task, instead of void, allows the main method itself to be awaited if called from another async context, ensuring proper handling of its asynchronous completion. This is a best practice for main methods in modern asynchronous applications, preventing the process from exiting prematurely while async operations are still pending. We're also setting the stage by printing a message indicating the start of our AI recommendation pipeline, giving a clear context to the demo. At lines 11 to 18, we see the core execution flow within our main method. The comment at line 12 is insightful. This is the hello world of async/await state transitions. It highlights that even simple await calls demonstrate the underlying state machine. At line 14, string recommendation equals await get personalized recommendation async, is the critical line. The await keyword here tells the compiler to pause the execution of main until get personalized recommendation async completes its asynchronous work. Importantly, this pause is non-blocking. The thread running main is released back to the thread pool to perform other work, preventing UI freezes in GUI applications or improving server throughput in web applications. Once get personalized recommendation async finishes, the control returns, and the main method resumes from this point, printing the result and signaling pipeline completion. This non-blocking nature is fundamental to building scalable and responsive applications. Now we dive into get personalized recommendation async, a method designed to orchestrate multiple asynchronous operations. Notice its signature, static async task string. The async keyword is again present, indicating it will contain await expressions. The task string return type signifies that this method will eventually produce a string result asynchronously. At line 22, we print a message, which executes synchronously. Then, at line 28, we encounter our first await fetch data async, user profile. This is a crucial point where the compiler transforms this method into a state machine. When fetch data async is called, it returns an uncompleted task. The await keyword checks if this task is already complete. If not, the current method, get personalized recommendation async, is suspended, and control is returned to the caller, in this case, main. The thread is freed. The continuation, the code after the await, is scheduled to run when fetch data async eventually completes. This mechanism is key to achieving concurrency without traditional, resource-heavy thread management. Lines 29 to 35 demonstrate the resumption of our asynchronous method after an await completes. At line 29, string user profile equals await fetch data async, user profile, has finished, and the user profile value is now available. The state machine, which was suspended, transitions back to a running state, and execution continues from line 31. We print the received profile, confirming that the asynchronous data fetch was successful. Then, at line 34, we prepare for another asynchronous operation, fetching the product catalog. This sequential await pattern ensures that user profile data is fully retrieved before we proceed to the next step, maintaining data dependency order while still benefiting from asynchrony. Continuing our journey through get personalized recommendation async, we hit another await at line 37, string product catalog equals await fetch data async, product catalog. This is another suspension point, identical in principle to the previous one. The method yields control, and the thread is freed until the fetch data async call for the product catalog completes. This pattern of awaiting multiple distinct I/O operations sequentially is common. While these operations are technically performed one after another from the perspective of this method's execution flow, the underlying thread is not blocked during the await periods, making the overall application more efficient. Once the product catalog is retrieved, execution resumes, and at line 40, we combine the two pieces of retrieved data to form our personalized recommendation. This final step is synchronous processing that occurs only after all necessary asynchronous data fetches have concluded. Let's examine the fetch data async method from lines 45 to 50, which simulates an I/O bound operation. Its signature static async task string indicates it's an asynchronous method returning a string. The most critical line here is await task, delay, 100. Task, delay is a powerful tool for simulating asynchronous work without actually consuming CPU cycles or blocking a thread. It creates a task that completes after a specified time. When await task, delay, 100, is encountered, the method immediately returns an uncompleted task to its caller, and the current thread is released. After 100 milliseconds, the task completes, and the remainder of fetch data async, the return statement, is scheduled to run. This is the essence of non-blocking I/O simulation. The thread is not busy waiting but is free to do other work, significantly improving application responsiveness and scalability, especially in server-side applications handling many concurrent requests. Finally, at lines 51 to 58 within fetch data async, we see the synchronous part of the method that executes after the task, delay completes. This return statement uses a C# switch expression to simulate retrieving different pieces of data based on the source parameter. This is a simple way to provide mock data for our demonstration. It's important to understand that this part of the code will only run once the await task, delay, 100, has finished. This ensures that any data retrieval logic, even if simulated, conceptually happens after the simulated I/O operation has completed. This entire fetch data async method serves as a perfect example of how to encapsulate a potentially long-running, non-CPU bound operation into an async method, making it seamlessly integrate with the await keyword and the asynchronous programming model. By scanning this code you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. This lesson is excerpted from Volume 4, Chapter 2 of the C# and AI Masterclass ebook series and from the volume Asynchronous AI Pipelines. Async/await, parallelism, and streaming LLM responses. You can find all source code here, https://github.com/edgarmilvis/C# programming series. The ebook includes 20 chapters, each one with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. Thank you for your attention. I look forward to seeing you in the next lesson.